what does this function looks like? That is the thing. If we put this as a coefficient m2, then m2 coefficient to this one is actually larger than 0 for t is larger than t, of course, and this is just too trivial, almost elementary school mathematics, but yeah. Because A2 is a positive. But this sign change provides a very important point. Basically, this function is actually this free energy as a function of m is basically the fourth order equation described as constant times linear term and quadratic term and fourth order term. And what we have learned so far is that this A2 can be positive or negative. To make our problem a bit more simple, let's consider the case of A1 equals 0. That will completely remove the odd term, so it will make the function even function, completely even function. Then this would correspond to a function like again. What does this function look like? Let's explore. Well, one thing for sure is that because A4 is always positive, it always diverges like this and like this. Okay, symmetry. Like this. It will always have this diverging, either positive or negative. And of course, it will cross C here, because if you put 0 there, you will produce C. And the important point is that then how does it behave in the middle? That is most important point. Of course, to look at the possibility of a behavior there, whether it will just goes like this or goes like this, how can you distinguish these two? That is the most important point. One thing you can try is, of course, in this case, you have this local minimum or global minimum. So let's see which case corresponds to which one. So if you take a derivative, you will have so whether it's possible to have this zero derivative or not. This is a Jodo's equation, but luckily we can actually get. Suppose we have this criterion. And one thing for sure is that, of course, it always has a zero slope here because it's a by definition of the even function. Yeah. But in this case, to have this some specific x star that will make this derivative zero is that the criterion is then like this. So x star squared is minus this one. And as I told you, A2 can be either positive or negative. If A2 is positive, then this one become negative. So you cannot have a real solution, except for the imaginary solution. So precisely, this part positive A2 would correspond to this red scenario because there cannot be any local minimum there. And in contrast, of course, if A2 is negative, then it's possible to have this real root because this overall vector would be positive if A2 is negative. So this would correspond to this case. And let's see what was A2 and A2 here. A2 was the complicated one, but the A2 below here is this M2 here. Sorry for the confusion. Then this corresponds to T is larger than TC, and the below is correspond to T is smaller than TC. And what was M here? The horizontal axis was M, in fact. I put it as an X, but it's really M. So it means that we have to minimize the free energy. And if I actually interpret this, if T is larger than TC, the only minimum is here, or M is equal to 0. But for T is smaller than TC, the minimum happened actually here. M is X star, which can be either, you should not forget that there's extra branch here as well, minus X star. And this is precisely what happened for this tangent, the crossing point of the tangent hyperbolic star. So what's really happening here, according to the textbook, this nice plot shows that for T is larger than TC, the only minimum happened at 0. while for t is smaller than Tc, the minimum happen at non-zero point. So this is a quite radically different approach, but still quite a insightful thing, because we come up with this polynomial instead of this complicated hyperbolic function and log of hyperbolic function. So as a result of Taylor expansion, of course, we lose the information of the detailed behavior, but still we fully recover the most essential part of this aspect. Depending on the sign of t minus tc, we will either have a zero order parameter as to minimize the free energy, or some non-zero value as to minimize the order parameter. And actually, this approach, actually, in some respect, this formulation could be actually better than some of the previous approach, because if you recall, in this case, for this t smaller than tc case, we can see that there are three solutions, but we just took for granted that these two are the real solution, not the zero solution. It was not possible to argue that the stability of the solution here, but now it's possible, thanks to the Landau theory, that this point, in the case of t is smaller than tc, is actually correspond to local maximum, not local minimum. So this is unstable solution. That is the most important point. So even if we lose all the detailed information about the free energy, we kept the most essential part that characterized the phase transition. And that is the most brave but quite insightful approach by Professor Landau. So how about we can actually re-put this H term, the external field. And of course this happened. Now, because of this H, the symmetry is broken now, because of this linear term. So in the textbook, it nicely illustrates each of the cases where so this middle law actually shows the situation that we have dealt with so far. But for negative or positive external field, the symmetry is definitely broken, and you can either have this point or this point or this point. But the thing is that when t is less than tc, when h becomes 0, this one, so let's suppose our solution, let's track our solution. So by changing the external field, the solution was here first, and then here. And from here, if we increase the h a little bit, even if it's tiny little bit, the solution just jump from here to here without the middle ground. So this is definitely the sign of the discontinuous phase transition. That this continuous phase transition can be also observed for this free energy, the Landau free energy. So it's quite powerful. It's very simple, but quite powerful. Compared to this point, if the temperature is larger than critical temperature, it will slowly move from here to here to here. So there's no discontinuous transition. So continuous transition here and discontinuous transition here, it all observed by this very simple but powerful Landau free energy term.